Hello everybody and welcome to another episode of the Physics Corner, a series of videos intended to help you set up and solve physics problems for introductory classes. I'm your host, Dr. Christopher Cirola. Today we're not looking at an individual problem so much as how to set up problems with some background knowledge, and that background knowledge will be unit analysis and units. So what is a unit and what is unit analysis, and what advantage do those things hold for us when we're trying to set up physics problems? So a unit is essentially a way of gauging the quote-unquote size of any particular number. So let's consider the following as an example, and this may make it a little more clear. Suppose I tell you that a distance, which I can symbolize with delta x, separate video to talk about that, by the way, equals 5. Your hopefully very immediate reaction should be, 5 what? Because it matters, right? 5 millimeters, 5 miles, 5 parsecs. It makes a big difference as to what you're going to have for an answer, unless you have some units attached to it, right? So that is something that's fairly important to include. So if I were to write, for example, something like this, I am inherently saying that the change in distance, which is what these symbols stand for, equals 5.0 meters. And then I have something I can talk about. Now I know approximately not only what the number is, of course, but also what the unit is telling me. So I have a feel for how large this particular distance represents. Without that knowledge, we're really stuck. We need to have units. Now, this is a caveat, there are sometimes in physics a few quantities that do not have units. For example, a coefficient of friction, which is something that you'll encounter at some point in your career here. But those are rare, far and few between, and they are derived from quantities that do have units. So we do know what those numbers still represent, and they have physical meaning. But without the units attached to a typical number for something like a distance or a time or a mass, it's very difficult to figure out what's going on. So that's the first part. So why we have units? That's why. Second thing we can talk about, what kinds of units does physics typically use? Now, this is something you'll be encountering as you go along during the semester, but we'll give you a little quick preview as to some of the more commonly used units. And so, first off, physics units typically are what we call SI units, or International Standard Units. Now, the reason the S and the I are switched is because the original usage of the word comes from French and not from English. And then it was System International, if you will, if I translate carefully. By the way, real quick trivia, the metric system, which is what this is based on, was invented during the French Revolution of the early 1790s. So this is going back a little over 2 centuries. And most of the world has adopted them ever since. America is one of those rather big exceptions. But in the topic of physics, which we are talking about, we will be using SI and or metric units, and then we'll have to translate back and forth. So, what are some sample standard units? Samples are, for example, the meter, which we can abbreviate with the little letter m. The second, of course, it's unit of time here, abbreviated little letter s. By the way, it is little letter s officially for the abbreviation for seconds. You might have seen it in older manuscripts or books as SEC, but S is how physics people officially abbreviate that. The kilogram, which is a unit of mass, kg, like that. Of course, there is a unit called the gram, but for a variety of reasons, the kilogram is the standard unit of mass that physics people use. Notice, by the way, that some things are not here that are not metric. For example, inches, feet, pounds, those sorts of things. Those come from what we call imperial, or more carefully, British imperial units. That's a whole different system. More or less, the United States has kept and adopted the imperial system for everyday use, which is why your speedometer in your car usually talks about miles per hour, and why if you get on a scale, it tells you how many pounds you weigh. But those are not the units that are used by most of the planet. We're kind of the exception to that rule. Okay. Anyway, here's some sample units. Now, these particular units that I've got listed here, you might call them basic or fundamental units in that you can't break them down into simpler things. So it's a little like a chemical element. If you remember your chemistry, an element, by definition, is something that cannot be broken down any further. Now, we know that's not completely true, but let's roll with it, at least into, say, the same kind of units. And so if you have a hydrogen atom, you can't break it down any further without destroying the hydrogen atom. It's even more so than that. You can't break down a meter at all. There's no further breaking it down. Now, to put that in comparison, to give you an idea of what you could do for breaking it down, let's suppose I want to express somebody's speed, and I might do that in, say, meters per second. Now, if I abbreviate that, by the way, m/s like this would work just fine. And meters per second is a compound unit, if you will. It is a combination of things that I could break down into meters and seconds, right? So that's all I'm saying. Nothing more, nothing less than that. But we have that. Now, sometimes there are physics units that are so either complicated or represent a fundamental idea that we tend to give them a brand new name. And so meters, seconds, kilograms are, if you will, original to the metric system. But there are other units that are built up from them. So for example, let's suppose I take meters and multiply that by, say, kilograms and divide by seconds squared like that. So kilograms times meters per second squared. That is usually referred to in physics as something called the Newton. And if that sounds familiar, it should. That is named after Isaac Newton, of course, the very, very famous scientist from long ago. Notice, by the way, when we're using a unit, the unit is not capitalized. If we capitalize this, that would be the person Isaac Newton. This is the unit, not capitalized. The symbol or abbreviation for the Newton would be capital N like that, for example. And so, for example, I could talk about a certain amount of force that's exerted on something being, say, now let's stay with the same numbers, it doesn't matter for our purposes here, equal to, say, 5 newtons. That tells me how much force is being exerted on some particular object or in some particular situation. All right. Now, with all this in mind, what do these things represent? So a meter, everybody is relatively familiar with a meter, or most people are. If you want to compare it to our imperial or English units, it's a little bit longer than a yard. A second, of course, is a unit of time that we're all very familiar with. Kilograms, most people tend to relate kilograms to pounds. That turns out to be not quite correct. Because kilograms are actually a measure or a unit that expresses a measurement of mass, and pounds actually express force or weight. And so they're not completely compatible. Now, if you live on planet Earth, which I'm assuming all of us do, then it turns out that you can do a shortcut and make a conversion, but if you're doing physics, you probably shouldn't, because that's not actually correct. Let's do things the right way. Okay. Second thing to talk about with this list is, what do these units, say, translate to for things that you might be more familiar with? And so if you are from someplace besides the United States, most other places, you're already growing up with these kinds of units, and so it's nothing unusual. But most of our audience, at least for this course, is here in the United States, familiar with the English units. So how do they, say, translate? So, for example, just as a couple of ideas, let's suppose I want to travel 1 mile. 1 mile is roughly the same as 1.609 kilometers. Or, if you prefer to get rid of the prefix, 1,609 meters. And if you round off to 1,600 meters in a lot of the demonstration type problems we'll do in these videos, then it's not a big deal. If you're doing a lab sort of situation or an actual calculation, then please use this more precise value. By the way, some of these conversions are rounded off already. This is already rounded off to some extent because they're not inherently based on each other. They're separate systems, and so they don't necessarily have direct correlations. In any case, so let's suppose, for example, that I said, I traveled a distance of, let's say 5 miles, right? All right. What would that be in meters? How would I get it to that value? Well, I would, and I'm going to round off here to make this easier on the eyes. Let's suppose we round it off to, say, 1,600 meters for every mile. Now, if you notice what I'm doing here as I do my conversion, I'm arranging it on purpose so that the miles here will cancel the miles here. In other words, miles in the numerator divided by miles in the denominator cancel. That is legit. Units can be canceled or made to square or square root or all the other various math functions that you're familiar with in manipulating numbers can also be used to manipulate units, and that includes dividing a unit by itself and canceling it, or if you prefer, making it equal to 1 so it goes away. Suppose I do that, then miles cancels miles. 5 miles times 1,600. If I'm doing my math correctly, that's 8,000. And so 8,000 meters would be my answer, right? So I can get that kind of result. Same kind of thing for a lot of other ideas then. When we want to, say, get a better handle on what a number refers to, especially if you're new to physics and you're not familiar with the metric or SI units, sometimes it would help to translate your values back into units that you are familiar with. And so let me give you another example. Let's suppose we're driving down the road and the speed limit is 35 miles per hour. And you're a conscientious citizen, so let's do exactly 35 miles per hour. Or at least 35.0 miles per hour, and that's probably about the precision that your average car is capable of anyway. By the way, it's V for speed, not S for speed, as you might expect. Different lecture, but in any case. Let's suppose we want to translate that into meters per second to figure out what that really refers to. So, first off, let me write it this way. 35 miles per hour, like that, okay? Now, in order to do a unit conversion, I want to get rid of the miles and bring in meters. I want to get rid of the hours and bring in seconds, right? There's a couple of ways to do that, but let me do this rather explicitly. So, again, I'm going to round off for our purposes here. So, for every mile, there's 1,600 meters. So, I would write 1,600 meters divided by 1 mile. And then notice, of course, that my miles will cancel and I'll be left with meters. How about the hours? Well, I could do this in 2 parts, but I think it's easy enough to say this. 1 hour consists of 60 minutes. 60 minutes, each minute, consists of 60 seconds, right? So 60 times 60, or 3,600, is the number of seconds in every hour. So let's arrange it this way. For every hour, there are 3,600 seconds, right? Okay. And again, if you look carefully, I've arranged this on purpose so that my hours here cancel my hours here. And I'm left with meters per second as my unit of choice. By the way, if we do this particular calculation, and it's always good to check my math on this, you'll end up with a number of about 15.6 meters per second. So this process, going through this, is what is called unit analysis. Analysis is just a fancy word for saying we're going to dig into the details. That's all it means. It doesn't really, we're going to break something down into its details. Nothing more, nothing less than that. So don't ever be thrown by that kind of idea, right? Now, to kind of wrap up here, a couple more things I want to do. I want to talk about a special kind of unit that shows up in physics quite often. Give you a couple examples of that. And one more way in which units will be useful for figuring out physics problems. So, first off, let's take a unit, or look at the units of angles in physics and see what they have to offer us. So, and again, most people are familiar with this. 1 full circle for an angle is 360 angular degrees, like that. By the way, I won't say angular degrees all the time. I hope that's understood. Here I'm saying it just to point it out because the degree can be used for other things, such as temperature, right? You can have degrees Celsius or degrees Fahrenheit, and that's definitely not an angle. But it's hopefully understood. That's what we're talking about today. So 360 degrees for a full circle. I think most people know that, right? But we can also express that as 1 full revolution, or 1 ReV, if you like to abbreviate. It's often done like that. And that is just simply, of course, means exactly what it says, one full circle. Or, and this is where the physics really comes into play, 2 times the famous number pi radians. And the radian is a special kind of unit. When we get to talking later on in the course about rotational motion and do some sample problems, then we'll come back to this. But for right now, it might help to remember, in order to remember this conversion, the old formula for the circumference of a circle. You might remember this, C equals 2 pi r. What's the 2 pi? That's the full circle in units of radians, it turns out. So it's might help to remember it that way. If you remember the C equals 2 pi r formula, you'll help you remember this particular conversion. And a radian, then, is a special kind of unit that naturally falls out. All right, so a couple things then. What is a radian itself worth in units that you're more familiar with? Now, this is a familiar number pi. That's the 3.1416 and so on and so forth number, right? That's that famous number that never repeats and keeps on going forever. It's the famous number you get when you divide the circumference by the diameter, so on and so forth. But that doesn't help because it's not exactly equal to 3 or exactly rounded off to some other number. It's 3 point and several other digits. So it's not exactly a whole number. Therefore, it's not, say, 60 degrees per radian as it might suggest. But how much is a radian worth? Let's take a look. So, let's suppose our angle is 1 radian, RAD for short for radian then. Let's use unit analysis to do our conversion. So that would be 360 degrees divided by 2 pi radians, like that, right? And again, on purpose, we've set up so the radians cancel radians that way. And when we do this conversion, and I'm going to go to the nearest tenth of a degree, we get 57.3 degrees. So that's what a radian is. It's a little bit shy of 60 degrees. So I already hinted at that. But that gives you a feel for how big an individual radian is. Now again, why do we use radians? It's because radians, for starters, is the standard unit of angle in physics, not the degree, not the revolution, or some other way of expressing the angles. It's the radian. Second, the radian is a natural unit. Nature itself dictates exactly what that number is worth. That's a discussion, again, we'll probably have at some other point, or your professor and lecturer will have at some other point during the semester. But for now, simply say that the radian is the official standard unit of angle in physics. Okay. One more example to go along the lines of angles that may tie into everyday life, because this one's sort of artificial. Let's suppose you're driving in your car and you're at a stoplight, or you're just started up and your car is idling at a certain rate. Now, not all cars have this, but some cars do. They have a dial or a gauge which shows off the speed at which the engine is moving, and that's usually expressed in terms of RPMs. So, or revolutions per minute. So let's suppose your rate is 1200 RPM. Again, this little fellow here, that is the Greek letter W or omega. We'll come back to that in future episodes. For right now, let's just roll with it to have something to talk about. But 1200 RPM, or if we prefer, 1200 revolutions per minute, like that. Okay. Let's use unit analysis to turn that into the standard units. What would the standard units be here? Well, angles have to be expressed in radians. The standard unit for time is seconds. So we need to convert the revolutions to radians and the minutes to seconds. And again, you could do this in a couple of ways or take some shortcuts. I want to show off how it's done in general today, so I'm going to go the long way around. So 1 revolution is the same as 2 pi radians. So let me arrange it so that I will cancel out the revolutions and keep the radians. Notice, by the way, depending on the example, the radians could be on top or could be on bottom, numerator or denominator, right? It depends on what you're trying to convert to. What are you trying to get, and what are you trying to get rid of as far as units are concerned? I want to express it in standard units. Standard units include radians for angles, so I want to keep radians and get rid of the revolutions, so I'm doing it this way. Same thing for minutes. Seconds are the standard units, so 1 minute is the same as 60 seconds, right? And same logic applies, right? So I have arranged it so I get rid of revolutions, I get rid of minutes, and I'm left with radians per second, and that will be the standard unit usage to express this idea of rotational motion that we're talking about here. And again, don't worry about whether you recognize rotational motion or omega at this moment. We're just simply showing off an example of how to do unit analysis and do it with units. If I do this calculation, so 1200 times 2 pi divided by 60, I get 126 radians per second. So this discussion here then is meant to illustrate how to take units of one kind and translate or alter them into some other form of units. Why is it done this way? Why not have everything already in standard units? Well, first of all, life isn't like that. Again, your car engine, if it shows this at all, is talking about RPM and not radians per second. Now, you maybe could make an argument it should do radians per second, but the fact is it doesn't. Same thing with any other thing that you often talk about in life, especially in this particular country. We need to, if we want to talk about physics, we need the standard units, but if we want to talk about relating it to what people are used to in everyday life, we need to talk about things like miles and hours and pounds and those sorts of things, right? So, last thing I want to talk about here is how can we know if a formula for some particular quantity is correct in the first place? And units can play a role in that. And so, suppose we have two formulas. Delta x equals Vt, or delta x equals At, like this. And the question is, which of these formulas is correct? And how can we figure these out? Well, first off, and this goes back to a different video, but first off, we need to know what these symbols stand for, right? So delta x is a change of distance, so a distance idea. V stands for speed, T for time, and A for a quantity called acceleration, all right? Second thing is we can make use of the units to see if they match up. So if x is a distance, then x should come in meters, right? So on the left-hand side, in both cases, we have meters. Now, over on the right-hand side, suppose we do the Vt formula first. The Vt formula says we have meters per second, and here I'm going to write out the words so it's real obvious what's happening, multiplied by the time, which comes in seconds. And if you look carefully, then, meters per second multiplied by seconds, seconds cancel, and meters match up with meters. Now, I'm not writing an equal sign because we're not doing an equals. We're not doing an equality here. But what we are doing is matching. We're making sure the units match up. If the units do not match each other, then whatever else is happening, that equation or formula cannot be correct. The units must match up. So, on the other hand, let's suppose we do this one over here. So again, meters is on the left. Now, acceleration comes in units of meters per second squared. And then, of course, time comes in seconds like that. Now, one of these seconds cancels, but not both of them. And so we would have meters per second over here. This does not match up. Doesn't match. So out of these two formulas, this one has a better chance of being correct. Now, it may be that there's some other number that you need to have, like a factor of 1/2 or 2 or pi or some other number that goes in front of the formula to make the particular formula you're working with exactly correct. And that units can't address that idea. But if the units don't match up, your formula doesn't match up. So, and what I like to tell students is this. Let's suppose you're in the near future taking an exam on physics and you've worked all your problems out. You're pretty sure you got it done right, but you'd like to check your work. How can you check your work without doing the entire problem again from scratch, from doing it completely over again? One thing you can do is check the units. If your units at the end of your calculation come out correct, then there's at least a chance you're in the right ballpark. You may not have everything perfectly correct, but you're at least in the general direction. If the units do not match up, if the units do not agree with each other, then it cannot be correct. So what else is going on? You know that the units are not correct, therefore the answer cannot be correct. Therefore, you need to go back and take a second look at what you're doing. So it's a nice hint for taking tests. All right, everybody, thank you for your attention. Technical assistance for this program is supplied by Cindy Galchow and Sophia Turner. Funding comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Cirola. Thank you, everybody, for your attention, and clear skies.